been 100 days of observations for James Webb, and we have been reporting a little obsessively about all of the new science, all of the new pictures. But the reality is that there's a ton of science that we haven't seen yet, that we're still in this intermediate stage where we're waiting for all of the science results to come out. But it's a living, breathing telescope now, not just an idea in some engineer's desk. And so I wanted to sit down and talk with one of the most influential people on the JWST project, and that's Lee Feinberg. He has been the optical telescope element manager for JWST for its entire lifetime, so about 20 years. He helped decide what the mirrors would be made of, what kind of instrumentation would go in, and has been overseeing the construction and now its deployment and the operations. So we talk about what it's like to run the telescope. What happened with that micrometeorite impact? What are they going to try to do to minimize the chances of that in the future? How are other instruments doing? And that's about half the interview. But you can see why Lee does this job, because he thinks big. And so we talk about what comes after JWST. Will there be on-orbit servicing for future missions? What about modular on-orbit construction? What will LUVOIR look like? And then we think about the telescope that comes after LUVOIR, bigger, faster, more powerful. And then it gets weird. And we think about the possibility of quantum telescopes and how next generation telescopes could allow us to see other Earths at megapixel resolution. It's a fascinating conversation, and there are going to be ideas in there that I had never heard before. I am now obsessed about, and I think you will be too. So enjoy this incredible conversation with Lee Feinberg, how Webb's doing 100 days later, and then what comes next in large space telescopes. Hi, Lee. It's good to see you again.
Yeah, you too.
So last time we talked, I think it was after the launch, but before the data was starting to come in. Now we just crossed 100 days of Webb observations. How is it going?
It's remarkably well is really the very simple answer. Remarkably well. In all the years that we were developing JWST, I mean, it seemed like we just always had things we were working, and if anything, we're surprised at how little there is for the engineers to do right now. And the science is just churning away 24/7. So it's wonderful, really wonderful.
So let's talk a bit about just like how productive this instrument is compared to other missions out there. Like you're out at the Lagrange point. You're not having to orbit around the Earth. You're not having to change targets. How does it feel like in tasking targets and accumulating the science and sending it back to Earth compared to other missions that we might be familiar with?
Yeah, I mean, I don't think a lot of people appreciate that Hubble, spent half its time looking at the Earth, because as it orbits around in low Earth orbit, and so really they have a complicated planning thing of having to constantly only be able to get roughly 45 minutes worth of science data, per orbit. So right away, JWST doesn't have that, being at altitude. I mean, we do have to consider, as we orbit around the sun, what's in our field of regard, if you will. And so we do have to plan targets based on time of year, but we're running 24/7. And really the limitation is just, when you do a SLU, there's some settling involved. And so the question is efficiency to start taking science from SLU to SLU. And, but things have been, as efficient as we could have hoped this early on, which is why we're just taking, we're doing many things a day, many observations. Typically they're a couple hours long each. And sometimes there's, 4, 5, 6 of these things. Sometimes there's one huge thing that's 18 hours long or something. But, Nonstop,
But
nonstop.
but to give people context, like if you're doing an 18-hour observation of some target, how would that compare to what trying to do something equivalent on Hubble might be?
Yeah, I mean, well, so right away you're losing half the time on Hubble. So you could just double the amount of. I mean, that's why like 5 years of JWST time is almost like 10 years of Hubble time in that sense.
But also,
Um,
it's a vastly more capable instrument,
yeah,
right?
that's just in terms of the time. But
Yeah.
then, yeah, I mean, the time it takes to get equal signal and noise, kind of scales with signal and noise. And especially on the signal side, the collecting area is so much larger. It's like 7 times larger. So you can build up signal a lot faster. And if you're background limited, you win by even more than the factor 7 because it's signal over noise, and goes with the square root. So we can do things a lot more efficiently. Now, that doesn't necessarily mean when we do a deep field that we're going to do deep fields that are shorter. Our first deep field, and this is what really, really got me excited, I have to admit, was that first, it was actually the data that was released July 11th in the White House, the first deep field. If you remember that image, that was 12 hours, okay? It was 6 filters. Each filter was 2 hours, okay? But that was the deepest deep field that's ever been taken. Whereas Hubble, when it did its ultra deep fields and stuff, some of those went on for almost a month.
Yeah.
And here we are deeper, and we did it in 12 hours. And since then, there have been some of these programs that were GTO programs. So like the principal investigator of the NIRCam team and the NIRSpec teams have this one program that they're doing this sky deep field survey. And, one day I'm looking and they're spending 18 hours that day, then 18 hours the next day, compared to we just did enough to show people capabilities. And even from that, we're doing follow-up spectroscopy. So.
Right. I mean, we keep writing stories on Universe Today about the most distant galaxy that's been found. And a lot of the observations that are being made as part of other surveys. And they're like, oh, and by the way, this appears to be the farthest galaxy that we've ever seen. Nobody has really put their back into it yet to go and like, let's find the perfect gravitational lens. Let's spend days examining this region. Let's find the most redshifted object we can put our sensors on. It's just been breaking records.
Yeah.
Well,
and remember,
by accident.
I think it was something like there's somewhere between 400 and 500 hours of the first year of this early release science. So the thing that you saw, the deep field, was part of the early release science, and it was part of that actually even was part of the initial ERO data actually. But there's also the stuff that's come out publicly that's early release science. But then there's the GTO programs, which is what the principal investigators get. And some of those are really spending much longer times. That's reward for, some of the scientists spending 20 years on this program but that data has not been, they get 1 year proprietary. Now I think we'll start hearing from it a lot sooner. But so the deepest stuff, I think we haven't really seen yet.
So let's talk about that for a second, right? Because I mean, I explain this as often as I can and as much as I can, that there's really sort of two kinds of data that are being gathered. There are surveys and fairly large collaborations where the information is just being published immediately. I think of like Cosmos Web and other things like that. But then there are proprietary time that have been assigned to astronomers. They get a year, but to give them time to do their work and publish their paper, and it won't necessarily take a year, but they have a year. What is the breakdown between the stuff that is coming out right away? We've been reporting tons and tons of stuff, but that's all just the stuff that's public. There's still a tsunami of science. So what is the breakdown really between those two, do you think?
Well, and this first year is pretty complicated, right? Because there was the EROs, the early release stuff that we released on July 12th. There's the early release science, which is director discretionary time. Now that's usually about 10% of per year is director discretionary. But the director, Ken Sembach, at the time decided that they were going to focus it on doing what's called the ERSs, and they actually got these proposals for them. And that was where I was saying it's somewhere between like 400 and 500 hours of this first year is just that ERS. And that's stuff that instantly, when it comes down, the data is available, and that's what you've been seeing predominantly. Then there's the GTO data, which is the stuff that the astronomers who, like, for example, the principal investigator teams who built the science instruments, they have teams that get what they call guaranteed time, and that gets the 1 year proprietary.
Yeah.
And then there's guest observer. And the guest observer ultimately makes up the large majority of what we do. But in this very first year, because we have, also the GTO time, it's a lot more, split. And I don't have the exact statistics, but I kind of pay attention day by day. And what I'm seeing now is, we're most of the early release science is, it's finishing up. A lot of it was intended to feed into cycle 2. The cycle 2 call's coming out in a couple weeks. So that's one of the reasons they kind of front loaded the early release science. And now we're more into the GTO and GEO, and it's kind of split between the two. There were some really big GTO programs, and a lot of the GTO program is front loaded in the first couple of years because, the scientists who worked on it, they kind of get it. And then, ultimately they'll fade down because it's based on hours that they get. But so we're sort of in that transition point more and more towards general observer, which are people who wrote proposals. Usually it's teams of people, but there's a principal investigator, got selected through a very competitive process, and they get 1 year. And so all of this is making it interesting as to how data is getting released in this first year, because people get 1 year. If their data is being taken now, you may not, in theory, they wouldn't have to release public results for a year. Now, they often do before that.
Yeah.
And the other thing is that the early release science that we did, for example, in July, looking at the deep field, they want to follow. Remember, they found all these possible, really early galaxies, really redshifted, possibly some of the earliest galaxies. But they want to follow up with spectroscopy. A lot of that spectroscopy is going to be taken in December or January. So and part of that is the cycle of having to wait 6 months before the target becomes available again. So, so there's this real mix of stuff. So you'll be seeing stuff throughout the year. But I think after about a year, a little more than a year, when GTO and GEO stuff start getting through their 1 year proprietary period, there's going to be a ramp up of science results as opposed to cool looking images and stuff like that.
Yeah. And I think that's the like I've been getting a lot of feedback from my viewers, and they're like, we love the pictures, but what are the ways that the JWST is changing our understanding of the universe, starting to answer some of these big questions. Mm-hmm. And that is the kind of thing, I guess, that we have to wait for, that process for the scientists to finish their observations, to write their papers, to get them peer reviewed, to get them published in journals.
Yes. And so the major breakthroughs in our understanding of the early universe really haven't come yet. But what is coming out is evidence that it will be able to do it. And there are cases, like they just released, I think the first time I saw a follow-up with near infrared spectrometers. They have a prism mode that does spectroscopy. They followed up this galaxy, like ZF11 galaxy, like that they found that was lensed, and just 2 days ago released the results of it, or a couple days ago, sorry. And, so we are starting to get spectra of these early galaxies. It was like the first real spectra that I saw. So it's too early right now. But I think it's possible in early next year we're going to start getting scientific results, and when that happens, you'll know, because if you remember back to Hubble, especially when we launched SM1 and SM2, the first servicing missions, what NASA does when there's something really scientifically important is they have a press conference with the astronomers, and the media come and they answer questions, and you're not seeing a whole lot of that yet.
No.
Because because a lot of what we're getting is stuff that demonstrates that we can see the first objects, and we have this. What was neat about the one I was just referring to is what they call a low luminosity galaxy. It wasn't the oldest galaxy. I think it was like maybe closer to 500 million years after the Big Bang, but it was low luminosity. So it was saying in prism mode and NIRSpec, you have the signal noise to see low luminosity. And now we want to go find the ones that were the very first ones, like you were saying. And so when we combine these, now when we find them in these bigger surveys that are being done as we speak with like the GTO programs, we know we've proven that we have the ability then to follow up and to look at the chemical composition and how things evolve, potentially see these early, large black holes. The black hole stuff, I mean, I'm not an astronomer, but, the more and more I read about these, supermassive black holes early in the universe and understanding how they form, I think that stuff is, when that stuff starts coming out, there's going to be press conference after press conference because it's going to be super interesting.
There was a paper that I just saw today that somebody was starting to think about ways to reevaluate how the building blocks of galaxies came together, what role dark matter played, the supermassive black holes, how all these pieces came together. It sounds like the story is a lot more complicated than anyone was ever expecting, which is like it always is, but it's amazing, and hopefully we'll actually see these detailed in specifics and start to remove a lot of that ambiguity.
Yeah. And one thing that I think I've kind of been thinking about recently, I don't know if you share this a lot with your readers or the viewers, is the degree to which JWST is really going to help us understand the evolution of the periodic table. Because, we always talk about the first stars and galaxies, but, if you just look at, take the early release up, the ERO data where we did the spectra, and, the very first stars have hydrogen and helium, but then there's these heavier elements that form. And then you get supernovas, and then you get even heavier elements, And so that's really the periodic table, going from, at the point of the primordial, sort of Big Bang era of nothing to when we first can see light, the universe was very simple. It was hydrogen and helium, reionization period. And so we're not only filling in like sort of stars and galaxies, but we're filling in how did atoms come to be? And we're also seeing in other stuff, these nebula and stuff, have more details of how certain molecules formed. And so it's not even just the periodic table, but it's even, molecules. And it's something that we used to talk about with JWST, sort of the evolution of from start to all the way up to life, But in the early universe, it's really more it's more the periodic table. And it was really noticeable when those results came out in July and you looked at the spectra and you can see how few atomic species there were in some of these really early objects, So I think that's pretty cool,
Yeah. And I think about, the thing that I'm always really excited about is the potential for Webb to get a glimpse of those first stars, perhaps through gravitational lensing or something, because we still don't even know, were they limited to the mass that large stars are today, or could they get tens of thousands of times the mass of the sun and explode like supernova, the likes of which we can't even comprehend? What's out there? And then the follow-on of the atoms that were created kind of depends on what those first stars, how they lived and died. Yeah. And we have none left today.
Yeah, exactly. And, these are really, really hard measurements. It's why we designed JWST, but I really don't think people appreciate, because it's almost painful for me. I have all these people telling me how they can build a space telescope cheaper. There's much easier ways to build a space telescope, and it's like they really don't appreciate. Most people just see the unfolding, and they think that was the hard part of JWST, was the unfolding. I got to tell you, from the telescope perspective, unfolding was about the easiest thing we did. It's basically some mechanisms and latches, right? And we've been doing mechanisms and latches at NASA for 30 or 40 years, maybe more, 50 years. But, we were cooling a mirror to 50 Kelvin that has to be stable to nanometers. And then we have to have really low contamination because we don't have a baffle because we had to cool it. And so we can't, for example, on the secondary mirror, our budget for particle accumulation was like a few tenths of a percent area coverage. Our pointing and control systems, 1 milliarc second, 7 times better than Hubble, and we needed at least 7 milliarc, but it's performing even better than we expected. But that required closing the loop with the guider. We do these things at, we're measuring things at multiple hertz and closing the loop at a hertz. All of that at 50 Kelvin. So like, for example, the fine steering wheel has these little actuators that are voice coils. They have to work at 50 Kelvin and be stable and not drift. The level of complexity to get all of that working, and then we get the results and we look at how good it's performing from an imaging point of view. Our requirement was to be diffraction limited at 2 microns, which is it's a criteria of image quality. It says how good is its telescope. So Hubble's problem was that it wasn't good image quality. We're almost a factor of 2 better than that. And that is significant scientifically because it means that when we have, for example, a galaxy or a star, we get more energy into the slit that we're spreading the light from. So JBIS-T was incredibly complicated, but it's working better than we expected. And that means the science that we're getting is better because for the same amount of time, we're getting a lot more signal. You see what I mean? You're getting a lot more signal and noise.
Yeah, I mean, you're starting to approach the limits defined by the laws of physics themselves, as opposed to engineering, which is exciting.
Yes.
And I think that's exactly. I mean, we want to see pretty pictures, but astronomers want to see spectra.
Yes.
And that's the difference.
And the spectra is that for the deep universe stuff, right? What was designed to do. Yeah, you go in with these filters. The filters are wide band. There's a lot of different wavelengths. They're wide bands, so they get pretty good signal and noise. But you really want to measure spectra. And whether it's early universe or transits is another case where, the planet only passes in front of the star for 4 hours, 6 hours, whatever it is. And so you only have a limited amount of time. So you want to get the highest signal noise at all these different wavelengths. And you want higher and higher spectral resolution to do finer and finer details. So it's a very, you want as much signal and as low a noise as possible. And so since we're getting more signal because the energy is tighter and you're getting more through, and the throughput of everything is higher than we had required in the system, we're getting better spectra than more signal noise. Now in the future, I think what this means is we're going to be able to do more with it. In other words, for a given observation, it might take less time, and that allows us to do more observations. But for this year, since it was already planned that we're going to do a certain observation for a certain amount of time, they're actually even getting higher signal noise in the measurements. And in some cases, that higher signal noise might be complicating things for them a little bit, to be honest with you, because, things might saturate and all that kind of stuff. So that's, but the funny thing about it is it's working so well, it's actually making them adapt.
Are you going to get those diffraction spikes on your spectra?
Well, the good news about diffraction spikes is you only get them from the really, really bright stuff. So
that's what I'm saying. Yeah, you're getting such a powerful signal of the atmosphere of a planet that you're getting these spikes appear.
Spikes appear, or more importantly, at the center of these bright objects, you might saturate the detector, and so you don't get something that looks like a star. You get something that just turns black because you hit the rail essentially. And in fact, the very first stars that we did at the end of wavefront sensing control, the star saturated, and it was like, here we want to show this beautiful picture, but we don't want a little black splotch in the little where we saturated, and it was because it was just we're getting so much energy in the core.
So a pilot puts in a request for a new aircraft, or it's asked for their feedback on an aircraft. They provide a list of features that they'd like to see in the aircraft. The engineers build it, and the pilot gets to sit in the aircraft and actually fly it for the first time, practically compared to the spec that it is on paper, and starts to learn the nuances and the way it behaves and the weird shakes and sounds that come from it. So what has it been like to pilot JWST for closing in on a year now, compared to, in your mind, what it was going to be like to operate it?
That's a great question. I mean, it has evolved as the year went along, early on, I don't think people appreciated the level of complexity when we were first getting those first results. You'd slew the telescope. This is a humongous telescope. We've never had something this big and this far, and it's, compared to like a Hubble. Hubble is this like stiff thing. It's, I kind of use like analogy of like, it's like a truck or a school bus. It's
Right.
It's just, you're just turning this big
Yeah.
thing.
It's a culvert is sort of the way I think of it. Like a big steel culvert.
Yeah.
Yeah.
Whereas here we had, this huge floppy, mirror and sun shield's really floppy. And then you have, how does the pointing system deal with that? We call it pointing and control. And, and then we have the whole issue of the guiding system, closing the loop with the guider. And, for the very first time in space, we had done these little experiments in the ground, but now you're doing it with real stars using catalogs that are imperfect, because the catalogs that we generate of the sky and that tell us where stars that we want to point at to close this loop, they're developed from typically like ground telescopes and things that don't have the resolution so sometimes you have a double star. So early on, a lot of what we were dealing with was all those kinds of things, the real engineering aspects of having a humongous telescope with all the sensitivity, kind of not, catalogs that have limitations. And so we were solving a lot of problems along those lines.
So does it feel like, I'm trying to feel like it feels like it jumps back a bit? Like I've, when you move a telescope manually and you point it at some object, and if the mount isn't really nice and smooth, it has this little bit of a kickback. So you overcorrect, and you're like, okay, I want to get this object in the middle of the field of view. So I overcorrect a little bit because I know how much it's going to want to kick back. And you just get comfortable and this becomes second nature. And is it a similar thing that you kind of know how it's going to behave as it wraps up its slew?
Well, so this is the whole thing. And again, it's part of this complexity I don't think people appreciate is, we have the spacecraft down here with this large tower, then you have the telescope, and we have isolation, to, reduce vibrations from the spacecraft. But, there's this whole engineering field of what we call controls and control algorithms that deal with all these things, that try and make it so that when you point something, you don't overshoot. And, even, people who build robots, like these first robotics teams in high school, one of the first things the high school teams learn is that when you have a mechanism that's deploying, there's a controller called a PID control, position integral differential, where you want that thing to wind up just in the right place at the end and not overshoot or undershoot or do this. This is the worst thing. Yeah. Well, that's on a very simple, stiff thing that's doing this, right? You calibrate, there's these parameters that you calibrate. Now imagine something as complex as JWST with all these different dynamic modes and all these different stiffnesses. Now things have gone cold, so you have the uncertainties and the material properties at these temperatures. All of that hit us in the face within a week or two. Like, we had a week to do this alignment step, yet all of that was hitting us in the face. And so like a big part of what was going on early in terms of understanding the system was that kind of stuff, and it goes all the way down to, you point the spacecraft with star trackers, and they have their own little engineering intricacies, and there's a couple of them, and that forms a coordinate system, and then you transform that, and then you do controls. And so a lot of the early phase was that. Now, fast forward, to May, we're fully aligned, then we're checking out stability. And by the way, stability is the thing that we will never stop investigating, because, you always want to put, the part of the telescope that no one talks about and is actually maybe the most important thing scientifically is how stable things are. Mm-hmm. And it's actually, and that, I a lot of times when I give talks, I explain to people the hardest part of building the telescope was the stability. And in our case, we actually have 18 segments that all have to be stable to nanometers as we slew around the sky, dynamically, thermally. And so that's a really, really, so we're constantly evaluating that. So we went through a whole phase maybe a month of just doing testing and calibration and saying, when we slew, how stable are things? Because if they're not stable, and you start using them to do science, you don't know whether the results you're getting are the results of the telescope or the results of the science. And by the way, it turns out the stability is phenomenal. So even though we're still looking at it, what we're doing is trying to push the performance for things like coronography, which really require a lot of stability.
But
but that was the next phase.
Yeah, I mean, I can sort of wonder though, right? Like, have you learned how to, again, back to that pilot analogy? I mean, you're going to do a big slew. You want to go from this target over to that target. You know that the reaction wheels are going to kick in and it's going to bring the telescope over, but it's going to cause various strains and loads on the different trusses. The sun shield is, going to ripple a little bit, and then even the mirrors, as everything deforms a little bit, will they all come right back into their place? So have you built up sort of best practices and efficiencies on how, you look at a slew and you go, oh God, can we break that up? Can we?
Yeah. The slew stuff's working really well. We got through that early and and it's not really, you always go after the thing that are most impacting you. You kind of triage. And so we got through so maybe there's a little bit to be gained in efficiency that we'll continue to improve on there. But a lot of what I'll tell you, this is what's amazing is we got through things almost on schedule. There was just so much behind the scene that we were doing and working nonstop to do that, because there were lots of things that we had to understand and solve and test, but we kept moving along. And really along the way, we kind of checked off each thing. I mean, the last thing, which you probably heard about, was micrometeoroids. That was the first thing which was really surprising to me, was that one. It was only just one micrometeoroid. I mean, we were getting them along the way, and we had expected them. Turning out the environment is actually pretty close to what we expected. But there was one that deformed the mirror slightly and put a little thing on the mirror, and that one created a larger deformation we expected. And that was the one, when you ask about understanding things, I spent more time on that issue than any other issue.
Really? Huh.
Up until a couple weeks ago, really, when I finally,
So if we were able to recover JWST, bring that mirror segment down, look at it in the lab, would it be obvious where that impact happened?
You probably would see on the surface a small, place where there's some coating that's not there and possibly a hole. I think that part would be obvious, but that's not the part of it that, I was focused on. And the team was focused on. The team was more focused on than locally the shape of the mirror. And if you put it in a cryo chamber and you measured it with an interferometer, you would see that the shape over a patch maybe yay big or something,
like about a foot across.
Yeah, it was, I think, a 150 millimeter radius.
Right.
That amount you could see it very. You need an interferometer. It's small.
Right.
And so you wouldn't see it by eye just looking at the mirror, but that's the part that we were really paying attention to.
So is it like ripples? Is it like a dent in, or is it more like it's kind of the mirror is rippling a little outward from where the impact happened?
Well, very locally, you could get what looks almost like a crater on the moon. So you get a little, there's a little hole and then it raises up, and then but what the issue is that then kind of comes down back to the surface that you started with. And that is a little bit of what we call a deformation. So it looks, for the mirror's point of view, it kind of looks like what we call mid-spatial frequency ripple. But it's just one sort of waviness to it. And again, it's small, but the challenge is, for me, the first thing I was thinking about is, how frequently will this happen? Because one was really, I would argue, you would not be able to tell by looking at the images that it happened, and it had almost zero impact on the science. But if it happened once every 3 months for 20 years, see, and the other thing is, it's actually even more than 20 years. It's like at least 20. I think people have been talking to even be potentially past 25 years. It's like,
really?
yeah. I mean,
That's interesting. More than 25 years. Okay.
Potentially. I mean,
Potentially.
we've been quoting at least 20 years, but we've been conservative in how we, do things. And
Classic
so,
NASA.
yeah, right. And so, in my mind, it was like, we had this thing that we don't know how frequently because it was a little bigger than we expected. We don't know how frequently it's going to happen. And then you couple in the fact that we're going to last over 20 years. It's like you put all that together. What does that imply? And so that's why we were paying so much attention to it. But what we concluded and what now having another 4 or 5 months have shown us is that it was a very infrequent, you actually do expect, if you look, and it was, I hadn't looked at the statistical distribution of micrometeoroids. Of course, we're 25 square meters, but over 25 square meters, every year or two, you do expect one that's bigger statistically. It's like a power law. And it happened to have hit in the location that was one of the worst locations on the mirror in terms of how it affected the mirror. And that gets complicated and stuff that's hard to get into here. But there actually was a locational aspect to it that statistically was unlikely to happen on the next one. So we got sort of doubly unlucky in a sense. I mean,
it was surprisingly big, hitting the wrong part of the mirror.
Yes. And so when you put all that together and you feed forward, you feel a lot better about things. But even with all that, there is some ways we can mitigate, to reduce the number. And that's what the team that I was on, we've been looking at. And and one of the ways is you can plan your observations to face away from the RAM direction where the energy is higher. The relative velocity when a micrometeor is coming at you is double, relative velocity, and that's quadruple in energy, right? Because it's kinetic energy. So
I just want to understand that. So, I mean, is there a direction that the micrometeoroids are mostly coming from?
No, it turns out that these, so there's different types of micrometeors, but the ones that we pay attention to are what are called sporadics. Well, let me say it differently. There is some directionality to where they come from. But the real issue is that when you face if you think of JWST, we can either face in the RAM direction, which is the orbital velocity vector of the spacecraft, as it goes around the sun.
Right.
You're either facing that way, that hemisphere, or you're facing away from the orbital velocity, which is what we call the wake direction.
Right.
So you can think of these two hemispheres. And the point is that when something hits you coming at you, it has twice the relative velocity. So even though it may be evenly spread in terms of statistics, it's going to be worse in this direction because it has twice the relative velocity, 4 times the energy.
So it's safest to look at objects in the wake, ideally.
Yes.
And so do you think that will go into planning out, say, upcoming years worth of observations to try and cluster things into the wake if possible?
Yeah, I think if you pay attention to our cycle 2 call, you'll see, we're still working our way through what the final thing will be. But the way that one would handle this is as part of the call to actually, have the astronomers essentially propose to point away when you can. Now, there are some things you can't do that because they're time dependent and you want to be pointing in this direction.
The dart impact.
Yeah, but it's a relatively small percentage. And so you can say, okay, those are fine. But when if I have the choice to find something this way or this way, and there's a 6-month difference, right? As you come around the sun, you could point, in this direction, or you come around, you point in the opposite direction. And so if you have a choice, why not do it in the wake direction? And so that's, I think, that's kind of what we've been investigating.
I mean, there are places that JWST can't point at. It can't point on the hemisphere that's pointed towards the sun and the earth and the moon.
Yes.
And it can't point directly perpendicular to them within a cone. But if you just wait, every part of the sky comes into play, right?
Yeah, exactly. And So we always have a limited, at any given moment, we have a limited what's called field of regard, because you can't point at the sun, you can't point at sun or anti-sun, essentially.
Right. Yeah.
There's a field of regard, it's like plus 40, minus 5 degrees, and then there's a roll angle. We have constraint. But then in theory, you can point ram direction or or wake direction with those cones. And so what we're really talking about is for those two cones at any given point in time, whether you're pointing wake or ram. That's the other aspect. And it's in retrospect, I think that was the one thing you ask yourself, is there anything we didn't think of as over the many years we worked on this thing? We thought of micrometeorites, we budgeted for them, but it's this very rare statistical high energy one. And relative to that question is like, if you ask me on the telescope, the thing I paid attention to in all those years, was there anything that we didn't think? And that was like the one thing I can point to and say, I don't think anybody ever raised that combination of factors.
Have solutions come to mind since then? Have you sort of thought about ways that you could have given it more micrometeorite protection and still fit within the fairing and the weight constraints?
No. I think for JWST we would not have changed anything. I mean, in theory, there's some stuff we could have done in the mirror mounting to maybe make us a little less susceptible. But JWST's open architecture with the sun shield is really driven by the need to cool the mirror. We're cooling the mirror to 30 to 55 Kelvin by using deep space, which is super cold, to, radiatively cool it. And so, you start putting a baffle around it, like the Roman Space Telescope has, and the Hubble have baffles, right? Well, for a warm telescope, baffles are fine. But when you're trying to cool something at 50 Kelvin, that baffle would be seeing the sun and it would warm up.
Right.
And how do you get something 50 Kelvin when you have a warm baffle? Yeah. So I don't think we have regrets. I don't think we missed something fundamentally there on a 50 Kelvin, 6.5 meter telescope. And I actually think, when you look ahead, if you looked at what the decadal recommended for the next two telescopes, one is IO-UVR, which is, mostly optical and UV with high contrast.
Right, LUVOIR, but web-sized. Yeah.
Yeah, web-sized. And then there's a far infrared, also 6-ish meter telescope after that. That far infrared one, I think the jury is out. They may probably still want to have a sun shield and use deep space to get within their active cooling, because they want to get down to like 48 Kelvin. So they may they probably will stick with this architecture, where, or at least some element of it. Whereas for the IO-UVR, I think, we actually, and on the LUVOIR concept, we were originally going to use a sunshade, which was really good thermally. But I think, it's making us relook at the idea of using a baffle, which is painful thermally, but buys you micrometeorite protection, which is why, Hubble and, these kind of, it's partly why we weren't as sensitive to this whole thing. Is if you look at most of the telescopes that we've launched that are big, they're baffled. And so we are the first open telescope, like of this ilk. And so that's in part why, we had all these great review panels and brought in literally the world experts from all these different space telescopes and ground telescopes. And nobody raised this because it really hadn't come up on a previous program like this.
So the other issue that seems to have gone wrong is on the Miri instrument, one of the modes was experiencing some additional friction. What's the status of that?
So there is a, review board that has been looking into that. And at this point, I think they do have what they think is a root cause. I don't know though that they've, I'm not exactly sure where they are and they have a way that they think they can mitigate it. I think I can at least say those things.
Great. Okay. All right.
An approach to mitigating, but I don't think it's been fully, announced and all that. And so, and I'm not the true expert in all that. So I'm not the right person to try and explain the details.
But does it just mean like all the observations that were going to be used in that mode of Miri have just been pushed back until that all comes back online? They'll
They stopped. I think there's three different wheels essentially. Filters and and gratings and prisms in MIRI. And so this was only one of the three wheels.
Yeah.
So they still could do all the science for the other two wheels. For this one, the MRS, medium res, they were holding off using it, when this happened. And so, the plan is to, based on now understanding it better, get back to the point that they can start using it. And, I don't want to get ahead of them and, exactly where we are, but I will say I'm, feeling more and more optimistic about that.
So now that you are, you've mostly stopped obsessing about micrometeorites, and where are you putting the bulk of your time now into, I guess, what comes next? What are you dreaming about and hoping for as everything moves forward, or what is the focus of your energy?
So a couple things. I mean, one is sort of capturing lessons learned, because, one of the things I'm really realizing is a lot of the people who worked on JWST, people are retiring. Not everyone's going to be around for the next one.
It's been 20 years. Yeah.
And, so part of it is capturing lessons learned. But, personally, I like to think about, I really like building telescopes. I don't, so I'm already thinking about the next one and taking the lessons learned from the things we're talking about, from stability to pointing to micrometeorites, and updating the architectures that we've been thinking about, and making use of those things. And one of the this may surprise you a little bit, but one of the things I'm actually putting a lot of attention to, I was just at the AIAA this week, which is a pretty interesting conference, but it tends to be more focused on, the lunar architecture, lunar and, commercial and human programs. But I'm really interested in thinking about designing the next telescope to be serviceable, the way Hubble was, but at L2.
Wow.
And I have to tell you, I spent a lot of time this week talking with companies that are doing the software for robotics and building robots and looking at the the infrastructure that people are envisioning for Gateway. And my mind was racing about what all this implies for the possibility of being able to make a serviceable telescope at L2, without, planning it truly from the beginning, and in particular, the scientific instruments. I really think, JWST, a lot of people ask this question, and I don't think they really ever understood. Just, we were really mass constrained and volume constrained, but really, we lightweighted stuff year after year just to get in the box. So and it takes mass to make something serviceable. And we were cryo, right? Which is a really difficult problem. People don't appreciate, how do you take an instrument out that's 50 Kelvin? NICMOS was the one instrument on Hubble that was cool, but it had this Dewar with like 70 layers of MLI on it or whatever, the 70 layer MLI, and even NICMOS had its issues with it. It's a hard problem to build a warm instrument with something cryo inside. And so, but this next telescope doesn't need to be isn't cryo. So it really lends itself to being serviceable. The whole field of high contrast lends itself to serviceability in terms of how difficult it is. And so I'm actually thinking architecturally more and more about that, and making sure that we influence the architecture of the groups developing the infrastructure, and at the same time think about our observatory so that we have the potential to take advantage. And by the way, there's also these big rockets that are really exciting.
Yeah.
The Starship and, SLS, they're all about to launch. And believe it or not, there are new companies even talking about building large rockets. I was really excited to meet people doing that. So, taking advantage of all that size and mass, and one of the ways is to build things that are serviceable and use a little mass for that. And so that's where my time is starting to transition to, is the next one, but from a lessons learned and an architecture perspective.
The idea that I found really exciting, someone at NASA is working on this idea for on-orbit construction of the telescope, similar to what happened with the International Space Station, with what's going to happen with the Lunar Gateway, that you could send the main hub and then send the bits and pieces of the telescope up, and the hub is robotic arms and just starts attaching and bolting on the various pieces. And then you're not mass constrained and you're not size constrained. You can just keep extending your telescope as you go. And also then the servicing sort of becomes a part of the puzzle as well. Do you think that JWST was probably like the last large single launch telescope?
I don't think so, honestly. I think I'm really interested in assembly as well. And I think one of the advantages of making the next one serviceable is by learning how to do things at L2, like semi-autonomous robotics at L2, and being able to stage things along the way. We are building the roadmap to be able to assemble. But where assembly really becomes important is when things are too big to do a relatively simple unfolding. I mean, yeah, it looks complicated to unfold JWST, but at the end of the day, every deployment worked. And especially if you take away the sun shield part of it, they're pretty straightforward, latches and hinges kind of stuff. And since what the decadal recommended was things that are more JWST size, and we have a bigger rocket with more mass, I think it's going to be really hard to make the argument for assembly for this next one or two telescopes. But I think the ones after that are where you're really going to want to do it. And I think that's one of the reasons we want to think about the next telescope, though, in the context of where we're going, not just for servicing, but also keeping the scalable nature of things. One of the beauties of the JWST architecture is it's scalable. You can add rings, et cetera. And so and then if we add in the servicing, I could see the long-term thing being assembly. And I think really after this next, optical UV telescope, what will ultimately come will be an assembled telescope that's 15 to 20 meters.
Yeah.
That, that's the real one.
Yeah.
That's the one we really want to do. That was actually the big, LUVOIR A was a 15 meter. But I'll tell you, that was really, really sporty to do that as a deployment.
And I can imagine at this point, with the budget and the timeline with JWST, to then say, and now we want to make something that's bigger and introduce a mountain of new technical risk. Yeah. I'm sure some people were going like, let's settle down.
Yeah. It's always a question. It's almost always a question of what's the most cost-effective way to do the science. And I don't, and I just don't see how it's likely. I mean, listen, we always should stay open-minded, and, maybe some, company with, a trillionaire behind it says, hey, we'll assemble it for free for you. You just never know.
Yeah.
But like
the guy who bought that bird company, he could, the Elon Musk can launch you.
Yeah, exactly. It's, so you always stay open-minded, but I think, when you break it down financially, which is, it's always about cost per, science per cost. I think it's going to prove that deployments are going to be the way to go. And let's not have something quite as complex as the sun shield. I mean, the JWST sun shield, what really made it complex was, there are 5 layers, and if you look at them closely, you just see 5 layers the size of a tennis court. But those layers there's a very particular surface shape to them. And it's a tension system, and each layer has to have a separation from the next one to get the thermal, and, it kind of gets larger as you go farther out and can't have certain ripples. It was very complex because of the cryo aspect of things. Mm. Believe it or not, like for the LUVOIR architecture where we had the sunshade, we were literally just talking about a simple blanket. And it was going to be, it didn't even need to be tensioned.
Get the sun off the telescope. Yeah.
Yeah. And that would have been a much lower risk thing. And so, so I think, when people talk about the deployment complexity of JWST, it was really mostly because of the sun shield and mostly because of the cryothermal challenges of it.
And so do other wavelengths, like if you're in the visible light, is that more forgiving of the instrumentation of the telescope alignment, or do you think those challenges are still front and center. If you're going to go like the heat issues are less important, and the thermal changes to the mirrors are less important.
Well, okay, so you don't need to cool the mirror to 50 Kelvin, but the real key to the real hard nut, so like cryo is the hard nut for JWST, the hard nut on the next one is what they call contrast. It's the fact that the bright star we want to block relative to the Earth at these long distances is about a 10 to the 10th ratio.
Right, the 10 billion.
Yes, 10 billion to 1.
Brightness.
And what we need is something that's stable to a factor of 10 better than that. So we call it contrast stability that's 10 to the 11th, okay? And so now you say, well, how does that ripple into how stable things are? The primary mirror, there are two ways to do that. One group proposed a sunshade. The Habex team had both a sunshade and a coronagraph. The LUVAR team just had a coronagraph. But if we just focus on the coronagraph, which is internal, and the star shade would be very far away and have to be very large. So let's just focus on the coronagraph. The coronagraph, in that approach, the mirror has to literally be stable to 10 picometers RMS, root mean square, over its surface over some amount of time. And that amount of time we used to think was 10 minutes. Now people are proposing ways that it might only be a few seconds. But so that mirror can't have ripples in it on those kinds of orders. And that means thermally it needs to be very stable. And so if we are going to put it in a baffle, this is a lot of what we've been thinking about, is if you do put a baffle, can you get how do you get the mirror stable enough with a baffle? With the sunshade, it was actually it was beautiful because we blocked the sun with the sunshade. And so no matter where we looked, we saw the exact same thermal environment, or almost exact same. But when you have a baffle, as you slew around, the baffle gets hit by the sun and changes temperature. And so now we're probably going to have to thermally control the baffle, or have a more elaborate baffle. So that's actually going to be, I think, the architectural challenge for the next one. That's the kind of stuff we're thinking about, is what's the most optimal way to achieve thermal stability. So we don't need cryo. We're not counting milliwatts of parasitics, but we need stability. And it turns out we can get there. And actually, we have some really clever ways that we're thinking about, and that's what makes it fun. And that's what we're starting to think about.
But it is nice to take one problem at a time. Try to minimize the technical risk that you're injecting into the whole system, as opposed to trying to go bigger and trying to solve these problems at that fundamental level. That would feel like a lot to take on. That would feel like shades of JWST development, where you're like, you want us to do this and do that?
Yeah, exactly. And the argument with assembly sometimes is, well, it reduces risk because if you have a problem, you can solve the problem and before you move on, as opposed to with JWST, it's like you had to be highly reliable. I will tell you this though, having lived through JWST, I have grown in my confidence in our ability to build deployables, because we did things differently on JWST in terms of the audits and the inspections and the thinking, of details, attention to detail in that area. And I think if that's one of the key lessons learned, is when you do deployables, if we follow these processes we developed for JWST, they were unique, by the way. I had never seen a program done the level of inspections and audits and, independent inspections at those during the final stowing, et cetera. I think if you follow that process, we now try not to do something quite as complex as Essential if you don't have to. But if there's some deployable, it doesn't worry me as much as it used to, because I feel like we've kind of demonstrated that as long as you pay attention to the details, that's feasible. Whereas, assembly, maybe you could fix it if it's broken. But now you have all these new things like the real thing is the interfaces. If you're trying to achieve a millikelvin stability and put two things together, what is the interface that achieves millikelvin stability and dynamic stability and kinematic stability? So assembly isn't going to be an easy thing, and it should be very careful where you do it. And like you say, it's about complexity.
Now, where do you think on the value of exploring dumber telescopes that are bigger? There's been a lot of really interesting ideas like rotating liquids in space that you can harden into the shape of a mirror. Ones where you combine the light from multiple fairly simplistic telescopes that over time, as you add more and more telescopes to the formation, you're getting the equivalent of a surface area of a vastly larger telescope. But the price you pay is you don't get that. You're definitely not going to get your picometer stability across the mirror interface. You're just going to have a giant, but you may have a mirror that is hundreds of meters across. Do you think there's value in going that direction, or do you think keeping it engineeringly tight is the better approach?
I think you have to look. So each of these have their unique scientific objectives, and from the science comes, the designs that work. So, if it's far infrared, where you're more tolerant on the surface, but you still need the aperture for signal, what's the right strategy there? There might be a little bit of room for a little creativity, but it's not going to be the stuff like liquid mirrors. I mean, most of the people who propose these crazy ideas have never built a space telescope, and they're only solving one little slice of the problem.
Right.
And then as soon as you go to repoint the telescope, or you want to work over a large bandpass, or you need dynamic stability, whatever it is, that's their technology falls apart.
Right. Can I make a big parabola is the question they're trying to answer.
Yeah. Now, so I actually think what you said is right, is that we stick with the engineering tightness. But where I really think as we get bigger, I look at what SpaceX did with economies of scale. I really think that the genius of SpaceX is they figured out how to make the same thing over and over and over, like automobiles, cheaply. And it's relatively simple, but they're using economies of scale all the way to the extent of 3D printing parts and how they assemble things, and then you get into process control. I think we need to eventually turn telescopes into that. So I could imagine, and by the way, the ground telescopes, look at these ELTs that Europe's doing. I mean, Rias has this factory that's completely automated that makes segmented mirrors. I don't know if you knew that. They take the mirror, they do the metrology, they bring it over to the thing that does the polishing, they bring it over to the metrology with robots, all autonomous.
Mm-hmm.
Imagine you were doing that for a 20 or 30 meter space telescope, that same sort of thing.
Or you launched 20 space telescopes that are roughly the size of Hubble that cost you only, say, a few $100 million to launch, and you give a lot of more time to a lot of astronomers.
Yeah, you could do that, but and this is where I come back to the science. What science are you achieving with separate telescopes? Because you remember, diffraction it's wavelength divided by diameter, and when they're individual telescopes, you get collecting area, but you don't get the diameter. You don't get the resolution.
Mm-hmm.
Now, you can get the resolution if you do interferometry, where you take separate apertures and then you combine them like a radio telescope does with a local oscillator. And we actually built what we call a wide field imaging interferometry testbed at Goddard at one point. I was very interested in this. And the place that makes the most sense is in the far infrared, because in the far infrared, the longest wavelengths, that's where the resolution is really a challenge. And so you really benefit by being really large.
Right. And you have more give and play in trying to line up your wavelengths as well, because the wavelengths are so large. I mean, the Event Horizon telescope does it all after the fact in radio waves.
Yes. Now, so my other little side thing, I work on a lot of these.
Yeah. This is what I want to hear. This is the good stuff.
But here's the one that's really going to blow you away. So now I get to like the end of the line. The really end of the line is, so Event Horizon uses correlation after the fact, time-based correlation, to make their images. But what you really want to do is do interferometry from things that are as far, on opposite sides of the planet. I've got a ground telescope here and a ground telescope here, or eventually maybe a space telescope that are really far apart. And people are now proposing ways to do that using quantum networks, where you capture the quantum states of the photons, you send the information through a quantum network, and then you do the quantum Fourier transforms at a local place after the fact. And believe it or not, people believe this is possible. It's going to need a quantum network infrastructure, which is yet another thing I've been thinking about for other reasons.
Right, but hold on. Let me just
yeah.
let that idea sink in for people's brains, right? That the problem, like the big problem with interferometry of visible light telescopes is that you've got to align the wavelengths up perfectly in real time, because you can't do it after the fact the way you do with radio telescopes. But there has been this technology, and I've reported on this, and it's that you can that using the quantum, and I'm not exactly the exact technology on this, but essentially you can do the same thing without having that for them to be. So you point one telescope on Earth at a target, you point one telescope in space at a target, you record for an hour, you then blend them at the quantum level, or using that as a checksum to line up your wavelengths again, and you pull that data out, and now you have an interferometer with the distance of the baseline.
Yeah, and what you're really lining up is the phase.
Yeah.
The phase, if you think of an electric, a sinusoidal electromagnetic wave, it's the phase of that you have to maintain phase in order to create an image. That's why it's that's why if you have separate telescopes, right, that are far apart from each other, the reason why you can't just combine the data together and make an image is because you don't have the phase information. And, typically when we take an image, like on James Webb, we create an image on a detector. That detector creates a two-dimensional pattern that's just pure intensity. There's no phase information. And so the whole thing about interferometry is to, you have these separate apertures, is to bring them together in a way that maintains phase, so that you can line up those electric fields. So, because otherwise what happens is you get things become incoherent and you don't get an image.
All right. Now, before I distracted you, you're about to blow my mind. So please continue on with what's next.
So you can build an interferometer where you maintain phase by using metrology, like lasers that go shooting across, and use the laser to measure the phase, and then you collect and make the images. That was the TPFI, Terrestrial Planet Finder Imager. We had proposals for far infrared to do the same thing, and there were even proposals to decadal to do that. That's one strategy, and there are challenges in doing that. Both in the metrology is very complicated, and there's a lot of losses in those systems. The real problem is there's a lot of diffraction losses as you propagate a smaller beam across.
Right, and that's how LISA is going to work as well, to detect gravitational waves.
Yes, LISA is going to do that, but LISA, remember, they just got these three proof masses, and they're just measuring, as the gravitational waves, or gravity affects the proof masses, and they move around. The one-dimensional interferometer is all they're measuring.
Yeah,
and they're closing phase by having a triangle.
So how do we not have lasers?
So this is what's mind-blowing, and this is what, I envision we should be working towards a future, which is when you have these separate collectors. If I don't just create an image at the collector, but you could think of it as capturing the quantum information. There's more information in a photon than what we typically capture. We capture intensity, right? But there's quantum information in that photon. There's polarization, there's phase, there is quantum physics that says you can capture more information using quantum methods. And for example, even like if you look at a quantum computer, and granted, these things are complicated, and most of these are done with cryogenics using impurities in diamonds. But what they do is they do it at the single photon level. So this is not something you're going to want to do with a bright source. But if you have a single photon, I can capture its quantum information by doing what's called a Bell state measurement. Bell state measurement is a way to capture quantum information. The only real negative of this approach is it typically is very monochromatic, meaning I can design something that works at one wavelength, but doesn't work over many wavelengths. Now, but what you can do is you can multiplex. So, eventually the idea is that people can make it a bunch of these. They're almost like local oscillators, like we use in radio telescopes, that capture the quantum state. And then if you capture the quantum state, you have a separate network that can teleport that quantum state. And what that means is I've got a quantum state here, and I can teleport that quantum state here and do the same from another collector. If I collect all those quantum states, I can then combine them. But what's truly remarkable, and this is the thing that really blows my mind, is in a normal interferometer, if I have, A, B, and C collectors, I have to interfere A and B, I have to interfere A and C, and I have to interfere B and C, and then put all that together. So it's a very linear, and if I have lots of collectors, it takes a lot of computation. With quantum, because quantum states are not binary, they're not zeros and ones, but they're 2 to the n power for each state, there's something called a quantum Fourier transform, which is the whole basis of quantum computing, that could take these quantum information and all at once do the Fourier transform like that.
Right. Instantaneously. Yeah.
Instantaneously. So can you imagine, like, every ground telescope on the Earth is connected through a ground network. They teleport their quantum states to the central place where I can do a quantum Fourier transform. And all of a sudden I've got the spatial resolution of D being the separation from one ground, thousands of kilometers apart. So,
and you've got more information than just the intensity. You've got the full quantum information of all the photons that have fallen on the detector.
Yes, which has the phase which has phase plus even more information than phase.
Yeah.
I can capture polarization and some other stuff.
So you've got a telescope the size of Earth with the ability to record far more information.
And now, through economies of scale, I can build segmented telescopes that are 20 meters big, and I can put them in space where I can make them, very stable, and then have these hundreds of thousands, 1,000 kilometers apart, connected through a quantum network. What can I do with that? I can make a high definition picture of the Earth. And so people say, like, how are we going to ultimately, because
do you mean this Earth or another Earth?
Other Earths.
Yeah. I can feel like producing a high definition. I could take one right now, but
no. I mean Earth like 10 parsecs away. I mean like an Earth around another star.
Yeah.
And, it actually turns out, people had proposed years ago this Life Finder and all that, where they wanted to create an interferometer that did that. So they had these huge collecting mirrors that would be, I don't remember how many kilometers away from each other. And then you'd interfere them together. But as I mentioned, interference has this diffraction loss and all these other complications. But if I use quantum networking to combine them now, so combine big apertures with quantum networking, that's really
right.
If you ask me where we're going in 200 years or whatever, 100 years, I think, and so that I'm always thinking in terms of where do we want to get to, because you'll want to be thinking, and so that's the real, I think that's a really interesting vision.
And like, unlike the idea of the solar gravitational lens, where you have to put your telescope out 1,000 AU from Earth and you only get one target, this is a telescope that's that powerful that can be tasked at many different targets. You just have to point the satellites in different directions and at whatever you want. So all targets become available to this network.
Yes, exactly. And I think quantum networking will start with ground telescopes. We'll start with ground telescopes, because quantum networking will be done for other reasons, for connecting quantum computers. The ground telescopes will make use of that, and then they'll be able to and they'll connect themselves. And there are sort of even smaller steps along the way that they can do that are maybe not as big. And so I think actually the ground telescope, because, if you think about it, for ground telescopes, what do you do after you build the 30-meter class telescope? It's not very practical to build a 100-meter telescope on the ground. These civil engineering problems are pretty hard. But the thing you can do is this. And so I've actually talked to ground telescope people, and there's some interest in this stuff, both in, first maybe a little more in interferometry because it's a little nearer term, but they're definitely interested in potentially making use of quantum networking. And there are people from ground telescopes that are looking at doing demonstrations.
I mean, I wrote a story on this, but I don't think it really sunk into me what this means. And now I'm obsessed, and I can see why you're obsessed. This now lives rent free in my brain.
Yeah. I'm so obsessed that I even spent a year and a half helping architect the first quantum networking demonstrations. Because you pretty much have, if you want to do quantum networking over long distances on Earth, space is the place to do it.
Yeah.
I actually left NASA for a year, worked at an undersea fiber optics company, and we were doing Raman amplification, and we were trying to connect, Asia to North America with undersea fiber optics. Well, that's one way to, and you have amplifiers under the ground every 100 kilometers or whatever it is that amplify this signal. Well, there's a really big difference between quantum and laser comm or fiber optics, which is you can't amplify a quantum signal. You can't have an amplifier. It's all single photon.
Right.
And because it's single photon, if you put it in a fiber, it's very low rates. And so quantum networking in fibers doesn't go very far. You might be able to do, some number of kilometers, 100 kilometers, 1,000, 500 kilometers. But if you really want to go across, the ocean, or you want to go across the country, the best way to do that is actually using space platforms. So I've been thinking about ways to build quantum networks that would connect quantum computers. And it enables a couple things. One is this, what we're talking about, which is quantum telescopes that are connected. But it also does some amazing, there's a whole separate topic of quantum computing and where we're going there. And I think quantum computing is going to do more for science than anything in my lifetime, because quantum computers can model physics in ways that we've never been able to, because physics is fundamentally quantum. That was what Richard Feynman pointed out to people. And so once these quantum computers exist, people are going to be modeling, they're going to be doing computational fluid dynamics with them. And then they're going to want to connect them, and they're going to need this quantum network. So we're going to do that. And then the ground telescope people are going to use that. And so that's what I see happening.
That's really cool. Wow. It's a fascinating glimpse into the future. And I really hope that we do get that megapixel resolution of other Earths. It'll be pretty astonishing for us to be able to have that level of view out into the universe. And it kind of makes you wonder, are the aliens looking at us with that level of resolution? They must be, if they're advanced. But Lee, it's been a pleasure talking with you. I know you're busy. You've got a telescope to keep an eye on, but also new telescopes to plan and new technologies to harness. So what is the best way if people want to keep track of the work that you're doing? How should they follow this?
That's a great question, because the JWST stuff we put out on the blogs.
Yep.
So definitely follow the JWST blog. For the new stuff, a lot of it we report on in conferences, the SPAE conferences. If you look at, I gave a couple papers actually in Montreal in July, and I think it was June. One on JWST results and one on work we're doing for ultra stable telescopes. And so, you can read the papers.
Right. So search for your name in wherever papers are distributed. Wonderful. Yeah. All right. Thanks, Lee. Pleasure to talk to you. Let me know when you've got that quantum telescope operating.
Well, or at least, the first steps along the way. I will let you know.
All right. Sounds good. All right. Take care.
All right.
Bye-bye.
Thank you. Bye-bye.
You can also get even more space news in my weekly email newsletter. I send it out every Friday to more than 55,000 people. I write every word. There's no ads, and it's absolutely free. Subscribe at universetoday.com/newsletter. You can also subscribe to the Universe Today podcast. There you can find an audio version of all of our news, interviews, and Q&As, as well as exclusive content. Subscribe at universetoday.com/podcast or search for Universe Today on Apple Podcasts, Spotify, or wherever you get your podcasts. A huge thanks to everyone who supports us on Patreon and helps us stay independent. Thanks to all the interplanetary researchers, the interstellar adventurers, and the galaxy wanderers. And a special thanks to Josh Schultz and Andrew M. Gross, who support us at the Master of the Universe level. All your support means the universe to us.